In this next section, we're going to talk about binomial variables. We're going to learn how to identify binomial random variables and recognize the conditions that are required for a situation to be binomial. We're then going to introduce the binomial probability formula and then learn how it can be used to calculate the probability of getting a specific number of successes across a fixed number of trials. And these types of problems, they appear in statistics whenever outcomes can be classified as success or failure. Now, when we define success or failure, this might be easier to understand as an experiment that has a yes or no result, or I call them a yes-no experiment. Where a binomial variable models situations where we repeat the same yes-no experiment multiple times, and then we count how many times that specific outcome occurs. So let's take a look at some examples of identifying binomial variables. So we're going to identify if this is binomial or if it is not. It says, which of the following choices can be considered binomial random variables? And we have some conditions that we must meet in order for a binomial variable to be considered binomial. The first condition is the outcome has to be classified as success or failure. The second condition is that each trial is independent of the others. And that's been sort of a recurring theme in these lessons is we're mostly talking about trials that are independent. There also needs to be a fixed number of trials. And then finally, the probability of the success has to remain constant. So if we're given a probability that has to be constant, or if, like in this example here, it's talking about rolling a die. In that case, the probability would be constant, even though it doesn't specifically tell us what the probability is. It would be constant if we're rolling a fair die. That would have the same probability. Okay, so let's take a look at some of these now. So the first one says roll a fair die 5 times and let X equal the number of rolls that land, showing a 4. So we know that the probability remains constant. The outcome for each trial can be classified as success or failure because what we're asking is for for A is it a 4? Yes or no? So A is a binomial random variable. For B, it's saying, is it a 4 again, except it's just using Y instead of X. So B would be true as well. And then the last one says, let Z be the number of dice that land, showing an even value. And so the question for C is it even? Yes or no? I should have written yes or no for our 4 question also. Okay. And each trial is, so C is also a binomial variable. Each trial is independent of the others. So what's happening is when we roll at the die one time, we get a solution or we get a result. And then we roll another time. That means that the first time that we rolled doesn't affect the second time. That means that they're independent of each other and they're not affecting the probabilities of the next thing happening. And in this example, it's telling us that we're rolling it 5 times, or we're rolling 5 fair dice 1 time, is what B says. C says roll 5 fair dice 1 time. So there is a fixed number of trials for these. Just notice that A is they're doing it 5 times one with one die, and then for B and C, they're rolling it one time, but they're rolling 5 different dice. So all 4 of these conditions are being met for this first example. All right, let's take a look at another one. This company has over 200 employees, 48% of which are male, and the company is going to randomly select 10 of these employees to attend a conference. We're going to let Z be the number of male employees chosen. And it's asking, is Z a binomial variable? Why or why not? Okay, so we're going to look at the conditions for the binomial variable again. Let me make this a little bit larger so we can see it a little better. So our first condition, um, the outcome of each trial can be classified as either success or failure. So the question is the employee male? Yes or no? So that's our success or failure part to this. And we can identify that by figuring out what is the question asking. So is the employee male? Yes or no? Okay. Is the trial independent of each other? This one is a little bit unique because in statistics, if a sample size is less than 10% of a population, trials can be treated approximately as independent. And this is a statistical rule of thumb. The reason that this works is because when a population is very large compared to the sample, if we remove one item, that barely changes the probabilities. So here we're selecting 10 out of 200 employees. So that's less than 10%. So we can assume independence even though it doesn't say it specifically. Okay, and the number of trials, there would be 10 trials. So that part's listed. And then it says 48% are male. And so our probability remains the same throughout with 48%. So in this case, this would satisfy all the conditions for a binomial variable, and we can say that Z has a binomial distribution. Okay, I thought that was one of the tougher ones because got to know about the independence rule there. Let's look at one more of these. It says, which of the following choices are binomial random variables? So we've got to look at all 3 of these and check our conditions for all 3. So instead of, well, I guess we'll check all 4 of them, but let's see if we can find any conditions that where it does not meet the conditions for a binomial variable. So for A, we're involving a standard deck of 52 cards, and we're randomly drawing 7 cards without replacement. We're going to let Y equal the number of aces that we draw. Okay, so without replacement, that means that it's, well, let's go to, yeah. So without replacement, that means that the probability does not remain constant. So if we draw a card and don't put it back, that means that our next time that we draw is going to be, our probability is going to be out of 51. And the next time that we draw a card, our probability is going to be out of 50. And the next time is going to be out of 49 because we're not replacing that card. And so the probability does not remain constant. So A is not a binomial variable. All right, let's look at B next. So it says, in a game of luck, a turn consists of a player continuing to roll a pair of 6-sided dice until they roll a double. Let X equal the number of rolls in one turn. Okay, so the key word here is until they roll a double. So that means that they're going to keep rolling these dice over and over again until they get doubles. So in this case, there is not a fixed number of trials. So B is not correct either. And then we do have to choose one choice. So C is most likely our answer, but let's double check what C is here. So it says 60% of a certain species of tomato lives after transplanting from a pot to a garden. Eli transplants 16 of these tomato plants. Assume that the plants live independently of each other. Let T equal the number of tomato plants. Good. So it tells us specifically these are independent events. So that's good. We can check that. Classify as success or failure. That's do the plants live? Yes or no. So that condition would be satisfied. He transplants 16 of these tomato plants, so there is a fixed number of trials. And it says 60% of these tomato species live when transplanting them from the pot to a garden. So the probability does remain constant. So C is our answer for this one. All right. So now we know what binomial variables are. We're going to look at the binomial probability formula next. And the binomial probability formula lets us find the probability of getting a specific number of successes across repeated yes or no trials. So we can find the probability of whatever we're looking for given a certain amount of trials. In this case, for example, one, we have a 60% probability. And our total times that we're going to flip the coin, I'm going to call that N. That's for our total times, 5 times. And then it says that which of the following would find the probability of Heather getting exactly 3 heads in 5 flips of her weighted coin. So now we want to know that K is equal to 3. And let me write the binomial probability formula. It'll make more sense why I've used these letters. So the binomial probability formula uses combinations. That's what this first part is. Times p to the power of k times quantity 1 minus p to the power of n minus k. All right. Now this first part, nk, that's combinations. And we talked about combinations in an earlier unit. So nk would actually be n choose k. So that's the same thing. It's just different notation. So it's just another way to write combinations. And just kind of a side note, these combination values, they also come from something called Pascal's triangle, which is a pattern of expanding expressions. Um, but for this lesson, we're just going to stick with the formula, and you can use either your calculator or the combinations formula that we discussed in, I believe it was Unit 8, um, on permutations and combinations. So this is the binomial probability formula. Now all we have to do is just plug in these numbers. And it doesn't want us to solve, it just wants to know which of these equations would tell us what the probability is. And so now let's take a look here. We've got n is 5, k is 3, probability 0.6 to the power of 3 times 1 minus 0.6 to the power of 5 minus 3. Okay, and we'll simplify this as best we can without actually solving it. And that's going to give us 0.4 squared. Okay, and then we're just going to find which one matches, and it looks like D is our answer for this one. Okay, so that one is not too bad. This next one, though, we've got some fractions here, so this is just slightly different, but we're still going to use our same formula. So let me write that formula again here. The n minus k. All right. So Robbie and Grace, they know there's a 1/3 chance that two players will tie each other in rock, paper, scissors. They plan to play 6 times against each other, assume that the results are independent. So it tells us independence. That's good. That means that we're dealing with binomial probability. And then we're going to let t represent the number of attempts where they tie. So we want to find where t equals 2. So in this case, our k is going to be 2. So we're just using t instead, but just to keep things consistent, I'm just going to use k. So k equals 2. Um, the total times that they're going to play, n equals 6. And the probability is 1/3. Or you can use a decimal, but I'd suggest using fractions, especially since we have fractions as our answer options here. So this is going to be 6 choose 2 times 1/3 to the second power times 1 minus 1/3 to the 6 minus 2. So now that I've got 6 choose 2 times 1/3 squared times 2/3 to the power of 4. And it looks like that is going to be answer choice A. All right. Um, let's skip that next one. We're going to look at how to calculate it now. So now we know how to write that formula. Now we're just going to calculate it and actually put the calculations in our calculator to find our answer. So this first question says that a college has 800 students, 10% of which are left-handed. And it says, suppose they take an SRS, that means simple random sample, of 4 students. Let X equal the number of left-handed students in the sample. What is the probability that exactly 2 of the 4 students are left-handed? Okay, so we're going to write our binomial probability formula and choose K minus P to the K times 1 minus P to the N minus K. So now we just don't have any multiple choice and we've got to solve it. So we're going to write the formula and then plug that into the calculator and then round to the nearest hundredth. So the probability that X equals 2, we're going to let that just be K again. So I'm just going to say K equals 2, N equals 4, and our probability is 0.1 or 0.10. Okay, so now we're just going to put this in our formula. 4 choose 2 times 0.1 squared. Sure, that looks like a 2 there. Times 1 minus 0.10 to the 4 minus 2. So now we got 4 choose 2 times, this is going to be 0.01 times 0.9 squared. So now we have 4 choose 2 times 0.01 times 0.81. And 4 choose 2 gives us 6. Let me put that in the calculator. And this is 0.01 times 0.81. And this gives us 0.0486. And if we approximate that, that's approximately 0.05 when we round to the nearest hundred. And this is the probability that exactly 2 of the 4 students are left-handed. for the probability that x equals 2. Or we could say the probability that k equals 2. We used k in our formula, but they just want it in terms of x. All right, so that's 0.05. Okay, let's take a look at another one here. And these do get a little bit tougher. Now we're going to look at one that doesn't say equals. We're going to look at one that says we want to find the probability that it's greater than some value. It says Layla has a coin that has a 60% chance of showing heads each time it's flipped. So it must be heavier on one side. It's not a fair coin. It's not a 50-50 chance of heads or tails. She's going to flip the coin 5 times. Let X represent the number of heads that she gets. What's the probability that she gets more than 3 heads? So we're going to start by defining what this means. So we're going to define what the probability of X is greater than 3 actually means. So we're going to say that the probability that X is greater than 3 is equal to the probability that X equals 4 plus the probability that X equals 5. So we're saying that the probability that she gets more than 3 heads is the same thing as the probability that she gets 4 out of 5 are heads, plus the probability that she gets 5 out of 5 are heads. So that's an equivalent statement there. Okay, now we're going to use the binomial probability formula to calculate these separately. So when we calculate these separately, then we can add them together to find the probability that X is greater than 3. So let's do that. We'll split this side by side here. So I'm going to write the formula again. We have n choose k times p to the k times 1 minus p to the n minus k. All right, so we're going to find where k equals 4 over here, and over here we'll do k equals 5. And so our probability remains the same for both, 0.60. And I like to just write all this out. It helps me to keep everything organized. And the number of times is 5 for both also. Okay, now we're just going to plug these in. We get 5, choose 4 times 0.60 to the 4 times 1 minus 0.60 to the 5 minus 4. And that's just going to give us to the power of 1 there, but we'll do 5 choose 4 times, actually, let me simplify 5 choose 4. Let's do this a little bit quicker here. So 5 choose 4 on the calculator is 5 times approximately 0.1296 times, and this is just 0.4 to the 1, which is 0.4. So we get for probability that X equals 4, that's equal to 0.2592. Now I went out a few extra decimal places, even though it says to round to the nearest hundredth, because when we add these together, it's always a good idea to go out a couple more decimal places and then round at the very end. That's just a good rule of thumb for any time that you're doing decimal rounding. It's just to go out a couple extra spaces, place values, and then round at the very end. Okay, so now we're going to do the second formula. 5 choose 5 times 0.60 to the power of k. Now k is 5 times 1 minus 0.60 to the 5 minus 5. 5 choose 5 is just 1. and 0.07776 is zero point 0.6 to the power 5. And now this gives us 0.40 to the power of 0. Anything to the power of 0 is just 1. So now we just have 1 times 0.07776 times 1 again. And that gives us the probability that x equals 5 is equal to 0.07776. Okay, now we're going to add these together. So the probability that x is greater than 3, we're just using this formula up here. We're going to add probability that x equals 4 plus the probability that x equals 5. So we get 0.2592 plus 0.07776, and probability that x is greater than 3 is equal to 0.33696. And now we're going to do the rounding. And I might have gone out a little bit extra on the decimals, but that's okay. And now this is approximately equal to 0.34 for our final answer. So a 34% chance that she gets more than 3 heads. Okay, let's try one more of these, because now we're going to look at the probability that x is less than another number, or less than some value, I should say. Okay, so this says that Ira ran out of time while taking a multiple choice test, and she plans to guess on the last 6 questions. Each question has 4 possible choices, one of which is correct. Let x equal the number of answers that Ira correctly guesses in the last 6 questions. What's the probability that he answers fewer than 2 questions correctly in the last 6 questions? So this says what the question is asking. Fewer than 2 questions correctly. The probability that the number of questions answered correctly is less than 2. So we're going to identify the variables, or define the variables again. Or more specifically, define what the probability of x is less than 2 is in terms of a probabilities of x equaling some values. So the probability that x is less than 2 is equivalent to the probability that x equals 0 questions right, plus the probability that x equals 1 question answered correctly. Because we want to know the probability of this person answering less than 2 questions. We're not including 2, just including if they did 0 questions right or 1 question right. Okay, we're going to do the same thing. We're going to split our paper down the middle and find the probabilities for each of these using the binomial probability formula. So I'm going to write that formula one more time. We have n choose k times p to the k times 1 minus p to the n minus k. All right, so for probability that x equals 0, n equals 6, k equals 0, and the probability is equal to, in this case, 0.25. Actually, in both cases, each question has 4 possible choices. So the probability of getting the right answer, 0.25, or 1 out of 4. And the probability that x equals 1, that he gets 1 question right. Again, there's 6 questions. This one is k is 1, and the probability stays the same, 1/4 or 0.25. Okay, So we're going to just plug in these numbers again. And by now, this should probably be fairly straightforward. I think the first part is probably the toughest part of these problems. But we're just going to plug all these numbers in now. So we get 6 choose 0 times 0.25 to the 0 times 1 minus 0.25 to the 6 minus 0. So 6 choose 0 times anything to the 0 is 1. And 6 choose 0 is also 1. Let me write that as our simplified for 6 choose 0. And just kind of a side note, uh, anytime you have any value, choose 0, it always equals 1. And that's because there's exactly one way to choose nothing, and that is by choosing nothing. So that's why we always get 1 for any value, choose 0. Now this is going to be 0.75 to the power of 6. And so all we have to do is find out what 0.75 to the power of 6 is in our calculator to get the probability of answering 0 questions correctly. Let me get 0.17797. And again, I just went out a few extra decimal places because we're going to round at the end here. Okay, for the next part, we have 6 choose 1 times 0.25 to the 1 times 1 minus 0.25 to the 6 minus 1. And 6 choose 1 is 6 times 0.25. That's just to the power 1 is 0.25. And now we have times 0.75 to the power of 5. Okay, and this becomes 6 times 0.25 is 1.5 times, this ends up simplifying to about 0.2373. And we're just going to multiply that by 1.5 to get the probability of answering one question correctly is 0.3559. Okay, and then our very last step is we want to find the probability of answering less than 2 questions correctly. So we're going to use the formula that we defined in the very beginning. And we're just going to add those together. So when we add those together, we get that the probability of x is less than 2. Let me just write it out. 0.17797 plus 0.3559. Probability that x is less than 2 is equal to 0.53387. And our question is asking us to round to the nearest hundredth again. And so that's approximately equal to 0.53. All right, so that's everything on binomial probability using the binomial probability formulas and finding probabilities of values that are either less than or greater than.